Have you ever stopped to think about electricity and magnets? They seem like
Yeah,
totally different things in our daily life, right?
absolutely. One pulls paper clips, the other powers your phone.
Exactly. But what if I told you they're actually, like, deeply connected? And that connection, it pretty much powers everything around us.
hmm
So today we're doing a deep dive into that exact relationship. Specifically, how electric currents actually create magnetic fields. We're going to break it down in a way that hopefully makes sense for everyone, even if you're just starting to get curious about
Yeah,
electronics.
totally accessible.
And we're drawing heavily from some great material, Jaejin Chobo Joryuma Jongbi by John Byung-chil. It's published by Gilbert Publishing,
Mm.
and it's really designed for, well, for beginners.
And our mission here really is to go beyond just saying what happens.
Hmm.
We want to get into the how and the why. Give you those moments where it just clicks.
Those aha moments.
Exactly, without burying you in jargon. Just the core ideas, clear and simple.
Right. So let's start way back. For, thousands of years, people thought magnetism was just, well, a property of rocks, like lodestone.
Natural pull, yeah.
It was just this weird fixed thing in nature. Nobody really connected it to, say, lightning or the zap you get from static electricity. They seemed like totally separate forces.
Different phenomena altogether in their minds.
But then, and this happens a lot in science, doesn't it? An accident changes everything.
It often does.
Here's where it gets really interesting. Picture this. 1820, Danish physicist Hans Christian Ørsted. He's setting up for a lecture.
Just a standard demonstration, supposedly.
Yeah, he wasn't even looking for a link. He had a battery, a voltaic pile, and a wire. Simple circuit. And purely by chance, he sees that every time he turns the current on, a compass needle nearby just jumps. It flicks and points sideways, perpendicular to the wire.
And that must have been just mind-blowing at the time.
Total.
Because think about it. For 2,000 years, these forces, completely separate files in the mental cabinet. Ersted's little observation, maybe something he almost didn't even notice,
Right.
it just shattered that whole way of thinking. It wasn't just a neat party trick. It was the first real proof that electricity could make magnetism.
Wow.
It basically kicked open the door for the entire field of electromagnetism. A whole new era, really. Imagine someone showing that, gravity could create sound waves. It's that kind of fundamental shift.
So Ørsted basically tells us what happens. Current makes magnetism. Check. But, just knowing that isn't quite enough, is it?
Not if you want to do something with it.
Exactly. To actually use this, to predict it, build with it, you need the how. Like, how strong is the field? Which way does it point? And that challenge, that fell to a French physicist, André-Marie Ampere.
Ampere, right.
He took Ørsted's observation and just ran with it. Did the hard yards with math, experiment.
He put the rigor into it.
Totally. And his achievement was massive. He didn't just explain it mathematically, which is impressive enough, but he also boiled it down into these really intuitive rules, easy ways to picture it. And the most famous one, the one we still use all the time, is Ampere's right-hand rule.
And Ampere's work was just so critical. It took it from, that's weird, to, okay, here's exactly how it behaves. Before him, you knew a field would pop up, sort of, but you couldn't map it.
No way to predict it reliably.
Right. Ampere gave us the tools to predict the shape, the direction, everything. And that ability to predict these invisible forces, that's the bridge from just observing nature to actually controlling it. It's like the difference between watching lightning and building a power grid.
Okay, let's unpack this rule then. Ampere's right-hand rule sounds complicated maybe, but it's actually brilliantly simple.
Surprisingly intuitive.
Its main job is just to tell you which way the magnetic field points when you've got current flowing in a wire. It's like a little directional guide for this invisible stuff. So first, imagine a straight wire, electricity flowing through it. The magnetic field it creates isn't just random. It forms circles around the wire, like ripples in a pond, but magnetic.
Concentric circles, yeah.
And these field lines, they're strongest right near the wire, and they get weaker as you move away. Makes sense. But the key question is, which way are the circles going? Clockwise. Counterclockwise.
That's the crucial part.
And that's where your right hand comes in. This is the neat bit.
The classic mnemonic.
Yeah. So grab the imaginary wire with your right hand. Now point your thumb in the direction the current is flowing. Let's say the current's going up along the wire.
Okay, thumb points up.
Now just naturally curl your fingers around the wire. See which way they wrap.
Around the wire.
That direction your fingers are pointing, that's the direction of the magnetic field lines circling the wire. If the current flows away from you, your fingers curl clockwise. Towards you, they curl counterclockwise. Simple as that.
It's such a clever, simple visualization for something you can't actually see. And knowing that direction, whether it's circling this way or that way,
Yeah.
it's not just for exams. It is absolutely fundamental for any practical use. Knowing a field exists is interesting, sure, but knowing its orientation, that's how you control it.
That's how you make it do work.
Precisely. That's where you get the ability to actually engineer things with it. Without knowing the direction, magnetism would still be mostly this mysterious force we couldn't properly tame.
Right. So what does this rule actually let us do? Beyond the hand trick, I mean. Where does it show up in the real world?
Everywhere, pretty much.
This whole understanding, Ampere's rule showing us the direction, it's the bedrock for making electromagnets.
Absolutely. Temporary magnets.
Yeah. Think about it. You wrap wire into a coil, pass current through it, boom, you've got a magnet. Using the right-hand rule helps you know which end is north and which is south.
Crucial for designing them.
Turn the current off. Magnetism gone. Just like that. This ability to switch magnetism on and off, that was revolutionary. It opened up possibilities people couldn't have even dreamed of before Ørsted and Ampere figured this stuff out.
That's exactly it. And these electromagnets, designed using Ampere's principles, they are non-negotiable for how electric motors work. Think about motors in your blender, your washing machine.
Electric cars, fans.
Everything that spins using electricity. They work because you're using electric current in coils to create carefully controlled magnetic fields. And these fields then push and pull against other magnets or other electromagnets.
Creating force.
Creating force, exactly.
Yeah.
Specifically rotational force. It's all about those interacting magnetic fields. And Ampere's rule tells you how to set them up to get the push or pull you need in the direction you need it. It's this invisible dance generating very real motion.
It's not just motors, though, is it?
Oh, not at all. I mean generators. Basically motors running backwards, using motion to make electricity. Same principles. Transformers that step voltage up or down for power grids.
Yeah.
Pure electromagnetism.
Data storage, like hard drives.
Yep, magnetic patterns written in red, those huge scrapyard cranes lifting cars, massive electromagnets, even things like MRI machines in hospitals rely on incredibly strong, controlled magnetic fields.
Yeah.
It all traces back to understanding that link between current and magnetism Ampere defined.
Amazing how fundamental it is. Okay, building on that. Let's touch on another concept. It sounds a bit technical, maybe. Magnetomotive force, often shortened to MMF.
MMF, yeah.
But there's a really helpful way to think about it, kind of an analogy to electricity.
It maps quite nicely, actually.
So you know how in an electrical circuit, voltage is like the pressure or the push that makes the current flow?
Right, the driving force for the electrons.
Well, magnetomotive force, or MMF, is kind of the magnetic equivalent. It's the push that creates something called magnetic flux.
And magnetic flux, well, for anyone new to this, you can think of it as a measure of the total amount of magnetic field in a certain area. Like how much magnetism is actually flowing through there.
Yeah, it's a measure of the magnetic field's strength and extent. So voltage pushes current, MMF pushes magnetic flux.
And what's really neat here is how well that analogy works. In electricity, more voltage means more current, right? Assuming resistance stays the same. Ohm's law. Well, similarly, in magnetic circuits, a bigger magnetomotive force, which you get by, say, having more turns of wire in your coil, or pushing more current through it that leads directly to more magnetic flux.
A stronger magnetic field, basically.
Exactly. More flux means a stronger, more extensive magnetic field. This parallel isn't just a handy teaching tool. It's fundamental for designing magnetic devices.
Yeah.
Engineers use this relationship to calculate exactly how strong a field they'll get, or how much MMF they need for a specific application. It's the Ohm's law for magnets, in a way.
That really helps connect the dots. So thinking back on all this, it's quite a journey, isn't it? From people thinking magnets were just weird rock.
Yeah, for thousands of years.
Ørsted stumbling onto this connection by accident, and then Ampere digging in, doing the math, and giving us this elegant, super useful right-hand rule. It really shows how observation plus rigorous thinking can just completely change our world.
It really does. It's a perfect example of how understanding these fundamental invisible forces isn't just academic. It literally reshapes civilization. That twitching compass needle-led step by step to us harnessing electricity and magnetism to build, well, modern life.
Yeah.
It really underscores the power of asking why. even about small, unexpected things. You never know where it might lead.
So maybe the next time you hear an electric motor whirring away, or, I don't know, stick a note to your fridge with a magnet, just take a second. Think about that invisible dance happening inside. Electricity creating magnetism, magnetism interacting, all precisely choreographed by rules like Ampere's. It's going on all around us constantly.
Makes you wonder, doesn't it? What other connections are out there, hidden in plain sight, just waiting for someone to get curious and do a deep dive to figure them out.